Okay, let's get started. So good morning and good afternoon to everyone who's joining. Thanks for joining the September Solver Seminar brought to you by ESEC, the Emerging Scientists and Engineers Council. Our first speaker will be Srikanta Mishra, Senior Research Leader in Critical Infrastructure, who will present on energy transition, why and how, a gentle introduction. And our second speaker will be Ken Sims, a lead materials scientist in advanced materials and energetics, who will present on developing Battelle's high throughput zeta potential measurement assay. The audio line should be muted upon entry, but please check and ensure that you're muted throughout the presentations. At the end of each presentation, we'll pause for questions. So if you have a question, go ahead and unmute yourself. You can also use the chat feature to enter questions there as well. So without further ado, I will turn it over to Srikanta Mishra to begin our first presentation.
Thank you, Brian. Good afternoon, everybody. It's really a pleasure to be here today in what feels like a swan song, as the saying goes, as I'm retiring from Battelle at the end of next week. It's been a wonderful ride over the last 13 years. And I have worked in a variety of problem domains, ranging from geological CO2 sequestration to shale oil and gas development to conventional oil and gas development. And my work has involved a mixture of computational modeling and machine learning. More recently, my work has shifted to the area of energy transition. And because this has been generating a lot of buzz, I thought I'd leave with a gentle introduction to the topic, and that's why I appreciate this opportunity to present a Solver seminar. So I will share my screen, and okay. I'm going to turn off my camera just to hide the distraction and put it in slideshow mode, get my pointer going, and we'll be off and running. So energy transition, why and how, a gentle introduction. So the narrative that I will pursue about the interrelationship between development, energy, and climate is fairly straightforward, and it goes like this. Economic development requires energy usage, which is dominated by fossil fuels and therefore leads to CO2 and greenhouse gas emissions. This contributes to global warming, which results in climatic impacts, thus requiring a new energy, low carbon paradigm. So let's start with where energy comes from. Historically, the global energy mix has gone through two major transitions and is positioning itself for a third major transition. So the first transition from biomass to coal happened around here at the beginning of the 20th century, when coal became the primary energy provider, supplanting biomass. The second transition from coal to oil happened around here in the 70s, after the Second World War, as large discoveries of oil and gas fields led to a surge in the demand for oil, and coal usage kept on dropping. Now, additional drops in coal usage have also been triggered by the shale revolution, which has added significantly to the supply of cheap natural gas and crude oil. However, what is interesting to note that the fossil fuel contribution to the global energy mix has stayed at about 80% since 1970. Now, more recently, a nascent transition to renewable energy seems to be in the making, and that is what we call the latest energy transition from high carbon to low carbon fuels. And that has led to the share of renewable energy doubling over the last 2 decades, but still fossil fuels continue to dominate. Now, why do we need energy? Well, human development depends on energy usage, and this relationship is well established. A widely used indicator of human well-being is the Human Development Index, which is a summary measure of achievements in 3 key dimensions. We have, first of all, long and healthy life. that is measured by life expectancy at birth. We have education, measured by the expected and mean years of schooling, and a decent standard of living, measured by the gross national income per capita. So if we examine the HDI for various countries in the y-axis against the per capita energy usage in the x-axis, we see a clear trend as revealed here, an exponential increase in HDI followed by a plateauing off, a leveling off at about 150 gigajoules per capita. Now, developed countries such as the US and Germany have plateaued in terms of energy usage and HDI, whereas developing countries such as China and India will continue to grow their energy usage along this trajectory in order to increase the quality of life as measured by the HDI. Now, energy consumption trends also reflect this divergence between the developed and the developing world, especially since 2000. And you can see that here. So when we look at primary energy consumption for China and India, clearly that's in a very different trajectory compared to what is happening for US, the European Union, and Russia. And we note that because the energy usage significantly dominated by fossil fuels, and the combustion of fossil fuels produces CO2, we see a comparable correlation between energy usage trends and CO2 emissions. So here, for example, you see China, and then you have India, and then all of the developed world is basically plateauing with respect to its annual CO2 emissions. But as a whole, the world emit something of the order of 35 gigatons, a billion tons of CO2 per year. China contributes about a third, the USA about half of what China does, and the EU and India are at about 50% of what the US emits. So now that we have seen the linkage between primary energy consumption and CO2 emissions, let's move on to the next part, which is the relationship or the linkage with global warming. And here we note that the current scientific consensus indicates a definitive link between global warming and anthropogenic emissions of CO2 into the Earth's atmosphere. And here I show the empirical evidence that indicates a near linear increase between cumulative CO2 emissions and global warming. So this sort of encapsulates a very complex phenomenon into the single graph that is very useful for decision making. And basically it says that if we look at the historical record, then we see this near linear relationship. That means for every 1,000 gigatons of CO2, the increase in global surface temperature will be roughly about 0.5 degrees Celsius. And then we can project it into the future by assuming certain scenarios going from very low emissions to very high emissions, and we can see what will be the projected temperature trajectory. And if we have a certain maximum temperature acceptable rise in mind, then we can say that, okay, that is the amount of CO2 that can be emitted beyond where we are right now. So that's why I say that from a decision-making perspective, this is fairly helpful. Now, further substantiation of the causal relationship between CO2 emissions and global warming comes from model studies that show that human effects dominate global warming as compared to purely natural effects. And so, what these studies reveal is that the observed global warming time series, which is in black, is quite different from the simulated natural effects warming in green, but matches the simulation results that include human effects as well as natural factors, which is shown here in the light brown trend. And also when you put it all together and say that what is the total human influence, and that's this bar, that seems to match up quite well with the observed warming. So now that we have these calibrated models, we can look at various scenarios to help explore the relationship or the nexus between emissions and warming. So here, for example, we have a number of different scenarios that have been used by the Intergovernmental Panel for Climate Change and the IPCC, ranging from the most optimistic to what's called avoid at all costs. So you have descriptions like, okay, what does this mean? It means that CO2 emissions will be cut severely. We'll get net zero around 2050. There's a shift from economic growth to overall well-being, resulting in a warming of 1.4 degree by 2100. Whereas if we look at the dangerous scenario, for example, countries are going to focus more on their own national security, and so CO2 emissions will double by 2100, and warming will be 3.8 C by 2100. So there are multiple pathways that can help us explore not just the emissions warming nexus, but also the climatic impact of these scenarios. And that's basically what I show in the next series of plots. This is what I discussed earlier with respect to global surface temperature change relative to 1850 to 1900 for each of those 5 scenarios. And then we look at the corresponding September Arctic sea ice area, which shows outcomes that are practically ice-free, not good. And then we see the acidification of the ocean. And once again, the trend continues unabated, especially for the high emission scenario, with a small reversal for the very low emissions. And then as we look at the global mean sea level change relative to 1900, that can lead to as much as 1 meter sea level rise in the high emissions kind of scenarios. So I would say that the takeaway is quite sobering, to say the least. Now we can also get an idea of the cost of inaction. What happens if we don't do anything? So we can look back and say that what do we know about the climate change related disruptions and their cost on the economy? And that is what we have in this particular chart from the US government. So as we look at the disruptions caused by things like drought and wildfire and flooding and winter storm and freezes, so basically, we see that in 2021, the cost approached nearly $500 billion. And this is going to get more and more as climatic extremes become more and more common. So unless emissions are mitigated and global warming is curbed, these expenses are going to be in the multi-trillion in the over the next decade. So where we find ourselves now is the recognition that global action is needed to limit climate change so as to mitigate the effects of impacts such as higher temperatures, more droughts, changing rain and snow patterns, wild weather, less snowpack, shrinking sea ice, thawing permafrost, melting glaciers, warmer oceans, rising sea levels, and increasing ocean acidity. So that has led to the Paris Agreement, setting forth the objective of holding the increase in the global average temperature to well below 2 degrees C above pre-industrial levels, and pursuing efforts to limit the temperature increase to 1.5 degrees C above pre-industrial levels to minimize climate change impact. So that's where the motivation for the Paris Agreement came, in recognizing that there is this linkage between emissions and global warming and climatic impacts based on the evidence to date. So in order to address these goals, so we've set a temperature target, and as we saw in the slide a little bit earlier, that means we need to manage the emissions with respect to how much of CO2 is being cumulatively added to what's already there in the atmosphere. And that has led to the possibility that decarbonization pathways are how we set our high-level strategies. And there are many such pathways. One of them is the Sustainable Development Scenario, or SDS, promoted by the International Energy Agency, that reduces CO2 emissions while also tackling air pollution, achieving universal energy access, and assessing implications for water. So in a way, trying to take a holistic approach at the energy climate nexus. And basically what this involves is taking a look at the trajectory of CO2 emissions to date, and then saying that if we follow the stated policy scenario, meaning that we continue along our business as usual type pathway, the CO2 emissions will keep on increasing by like so. And then if we really want to make a meaningful dent in global warming and CO2 emissions, we have to add other aspects, for example, energy efficiency, renewables, fuel switching, nuclear, carbon capture, utilization and storage, etc., that will lead to a net zero by 2070. And that corresponds to a warming of 1.8 degrees C by 2100. So what does this mean in practice? Well, what we need is a multi-pronged energy sector transformation with increased contributions from wind and solar generation, electric car fleets, energy productivity, which basically means that that the economy becomes more and more efficient in terms of what is the GDP corresponding to every a barrel of oil equivalent, or every measure of how the energy usage is noted. Then we have the deployment of carbon capture, utilization, and storage. Um, And finally, the share of non-fossil energy, which should double from where it is right now, going from about 20% to about 40%, if we are to accomplish all of the objectives in the sustainable development scenario, which is what? Which is net zero in 2070, and a total warming of 1.8 degrees C by 2100. So let's take a look at some of the enabling technologies, such as carbon capture, utilization, and storage, or CCUS. This involves capturing CO2 from a stationary source, such as a power plant, an ethanol plant, refineries, or chemical plants, cement, steel plants, natural gas processing facilities, in a carbon capture facility, and then injecting into the subsurface for long-term sequestration, either into a deep saline aquifer or into a formation that is a depleted oil field, where CO2 can be used for enhanced oil recovery, or it can be used just for pure storage. Now, CO2 can also be captured directly from the air. This is called direct air capture. And Battelle is one of the established R&D leaders in this space, and now has a carbon services division serving commercial clients, and has also received a recent award in terms of developing a direct air capture hub. Another enabler of clean energy is hydrogen, either as a feedstock or for end use in industry, transport, and energy sectors. Here we see the hydrogen value chain, beginning with the generation of electricity from renewable sources that leads to surplus electricity because of the imbalance between the intermittent generation and the demand. So that surplus electricity can either be fed to the grid, or it can be converted to hydrogen by electrolysis, and then stored in the underground until it's needed for any application. Hydrogen can also be blended with natural gas, and put in the natural gas pipeline network, stored in the surface. And we also have a situation where hydrogen production is done in conjunction with conventional power generation, and one of the outputs is CO2. And if that CO2 is captured and sequestered in a CCUS type pathway, then this hydrogen becomes what's called blue hydrogen. Otherwise, what comes out of this is green hydrogen, because no CO2 is released during that process. So Battelle is also involved in the development of hydrogen hubs, which are regions where hydrogen end users and producers are co-located. This helps lower infrastructure needs and reduces costs. The US Department of Energy plans to spend something of the order of $8 billion for funding multiple hubs across the US, and Battelle is leading the way as the prime for 2 shortlisted candidate sites. Now, another key technology involves the sourcing of critical minerals. In the new scheme of things, when we transition to the new energy economy with, say, for example, a doubling of non-fossil energy sources, what we need are things like lithium, nickel, cobalt, manganese, and graphite for batteries, rare earth elements for wind turbines and electric vehicle motors, copper, silicon, and silver for solar panels, and copper and aluminum for electricity networks. However, the extraction of these is geographically concentrated, but we'll get that in a minute. First, let me show you the usage of these minerals and how it's expected to grow significantly to support decarbonization in the next several years. And that sort of brings us to the question of where are we sourcing these from countries like Chile, Indonesia, Congo, China. And not only that, but the processing is also quite concentrated in countries such as China. So from a national security perspective, it becomes critical to figure out how do we get these minerals from other sources. And Battelle is working to extract, upgrade, and separate these minerals from other feedstocks for diversification of the sourcing. At the end of the day, it's not just a simple technology problem, but it involves the so-called energy trilemma, which has conflicting goals. So energy must be sustainable for the environment. It should be affordable to consumers and has to provide security to the nation. And that is a complex, multidimensional challenge involving technology, economics, and geopolitics, which requires political will, a forward-thinking vision, and is certainly above my pay grade. So I'll just leave it at that, saying that, yes, we're working on the decarbonization part from a technology standpoint, but there are other dimensions to the problem. That's why it's the energy trilemma. So that sort of takes me to the end of my talk. And as I get ready to say goodbye to Battelle, I'd like to reproduce the dedication from my latest edited book as a gesture of appreciation to the mothership. So the book is Machine Learning Applications in Subsurface Energy Resource Management, State-of-the-Art and Future Prognosis, a compiled volume. And it's dedicated to the engineers, scientists, and technicians of Battelle Memorial Institute, all of you, 90 plus years of history and tradition in applying science, technology, and analytics for the benefit of mankind. So with that, I'd like to thank you for your attention. I hope this was a gentle and balanced introduction to energy transition. That is generating a lot of buzz. Thanks to the organizers for giving me this forum to present my last lecture at Battelle, and I will be happy to take any questions.
Thank you so much for that talk. That was fantastic. And congratulations again on the upcoming retirement. Are there any questions from any of the attendees today? Okay, so I will start you off with a question.
Sure.
You mentioned a number of the barriers toward global action and limiting climate change. In terms of the obstacles that are faced globally, do you see, I suppose, do you see the adoption by larger corporations, by governments, by individuals, but do you see any of those as being sort of the main driver toward limiting CO2 emissions? So you mentioned in the potential outcomes that we could see, if one of the options was if countries are more focused on their own needs and national security, that would probably drive up CO2 emissions. So that makes it, to me, that sounds like more this is government driven, but a lot of times, with at least things I've heard, corporations drive a lot of the CO2 emissions that we experience today. Where do you kind of see that as where we stand and where we're going?
Yeah, I think that's a very good question. I mean, on the one hand, there is a lot of awareness with the companies in terms of doing their part to reduce their carbon footprint and reducing emissions. But at the same time, you look at countries like China and India, which are significantly big contributors to the overall level of emissions. And the question is, they have to do something to improve the quality of life of their citizens, which means uh, providing access to cheap and reliable energy. So it's a very hard balancing act. I mean, what is their incentive to switch from cheap coal to more costly solar power? So who has the obligation to help them on this pathway? And that is where I think coordinated political and not eco, so political economic actions need to be taken at a global level. Otherwise, I think where we are likely to end up is what I would call what's called the middle of the road scenario. Income and development will grow unevenly across the world, and the progress towards sustainability will be slow. CO2 emissions will be stable and then they will start to fall, but not right away by 2050. And the warming will be 2.7 by 2100. Because, in many cases, people don't feel the urgency. I mean, they see that climatic extremes are really becoming more and more prevalent, but they don't feel that, okay, it's going to affect me unless you're a small island in the Pacific and you're going to get submerged.
Yeah, I think that's a really good point. For at least for many of us living in Central Ohio, rising sea levels is not something we're overly concerned about. But um, I guess kind of building off of that, in your expertise and um, depth of knowledge in this area, where do you? I guess how do we as a society continue to push toward not taking action until it's too late and trying to get ahead of um, sort of the dangerous and avoid at all costs scenarios that you have on the slide there? I know that's not an easy question.
Yeah. I mean, some of these things are going to be influenced by government, and in the Inflation Reduction Act and the bipartisan infrastructure law, a significant amount of money has been set aside to facilitate the adoption and the deployment of these technologies like direct air capture, like hydrogen hubs, like carbon capture utilization and storage. So there is government incentive to do things like that. For example, there is a tax credit of X dollars per ton of CO2 that's stored underground, depending upon whether it's an enhanced oil recovery project or a pure storage project. So ethanol producers who produce almost pure CO2 and the cost of capture is very low see it as a no-brainer of doing something. So if there is an economic incentive, whether it's market driven or whether it is based on government policy, that will go towards initiating the adoption, and sometimes success just feeds itself. Like the adoption of electric cars, if you have charging stations along, say, for example, I-70, you'll have more people driving Teslas and what have you. And if you have charging stations for refueling hydrogen tanks, then you could probably have hydrogen fuel cars as well. So sometimes it takes a little bit of a push, and this is where the political will from the current administration or future administrations is going to be very important, particularly in the U.S.
Yeah, absolutely. So I have a question from the audience for you here.
Sure.
How would you respond to some of the common arguments or skepticism raised against some of the evidence you present? Obviously, across our society, not everybody agrees with some of the climate change arguments here. So I guess how would you respond to those in general?
Yeah, I think my response is when you have 95 people on one side of the room who agree with the evidence, and then there are 5 people on the other side of the room, clearly there's an asymmetry in the evidence that points towards one side of the story. And if you start establishing a false equivalence by saying that every time there is somebody raising an objection that I have an objection, it really shouldn't be given the same degree of credibility. And the point I would make is the concept of outliers when you're doing linear regression. All of us have done that. We know that if there is one outlier, that one outlier really should not be given the same degree of same weight of evidence as all of the data points that follow a well-established trend. So yes, there are people who are skeptics, but being skeptical and then providing conclusive, credible evidence that goes against what is the accepted consensus, I think, are two different things.
Yeah, it's a great answer. So we'll give you one more question here real quick.
Sure.
Do you think there is any hope of reducing dependence on critical minerals such as lithium that can have negative effects on the environment and energy security?
That is a very difficult question because on the one hand we say that okay, we can see that renewables need to increase, but what is hidden behind that strategy is the dependence on critical minerals. So where exactly are we going to source those from? This is where I think the work of organizations like Battelle can become important. That yes, lithium maybe not mined from ore resources, but perhaps developed as a byproduct, as an extraction from other feedstocks. So that is the kind of technology that needs to be developed beyond the TRL 1-2 level. And the other aspect of that is perhaps there needs to be a paradigm shift with respect to the utilization of lithium per se in the processes that are going on. So how do you wean yourself from lithium in the first place, meaning that you reduce your dependence on that?
Great. Fantastic. Thank you for that. And thank you for the great presentation. So with that, we will turn it over to our second speaker today, who is Ken Sims. So Ken, feel